So here I am going to teach you the subject pulse and wave shaping circuits. Now, what is this subject all about? What are we going to learn in this subject? This subject I'll be dealing about two main things. One is generation, the other one is processing. Generation and processing of non-sinusoidal signal. So you have to be very clear in this subject. Here we are not going to deal about any sinusoidal signal generations or any processing of sinusoidal signal. Of course, for understanding a circuit, we will first analyze it with the sinusoidal signal, but that is only for understanding purpose. We are mainly learning the subject about generation and processing of non-sinusoidal signal. They can be categorized as pulse, digital, and switching waveforms. Now, these are the non-sinusoidal signals. That is our main concern. They find wide applications in the field of computers, counting and timing systems, data processing systems, pulse communication, radar, television, and also in many experimental research. So, here the methods are presented to you in generation of very narrow pulses. Very narrow pulses in the sense pulses whose width ranges between nanosecond and microsecond. Very, very narrow pulses. Or we will also be learning about generation of wider square waves. Wider square waves in the sense they are going to have a pulse width that ranges between millisecond and second. So the main category of wave generation or very narrow pulses or wider square waves. So apart from this, we also will be learning about generation of variety of other waveforms. They include step and exponential, pulse, chord, linear ramp, and so on. So it's mainly step, exponential, pulse, and linear. So these are the main category of signals we will be analyzing, we will be learning on how to generate. Now, after a pulse being generated, a waveform must be processed in some way or other in order to perform a useful function. Whatever we generate cannot be used as such. It has to undergo a processing. So processing can be anything. Maybe it can be transmitting from one point to another, or we are going to select a portion of it in voltage, or we are going to choose a section of it in time, and so on. Okay, we have a waveform, we'll just chop off certain portion and we'll only consider certain portions. So chopping off in time, chopping off in voltage, anything can be a processing. All these processing also will be studied in this subject. Okay, now talking about this major domain, the very important concept we need to understand now is linear wave shaping circuit. Linear wave shaping circuit. So our title of the subject is pulse and wave shaping circuits. In that, the very important category is linear wave shaping circuit. Now, what is this linear wave shaping circuit? Now, in the terminology itself, you can understand linear in the sense the circuit is made up of linear elements. Wave shaping in the sense this circuit is going to shape a given input signal. So I can define it in this way. It is a circuit which is made up of linear elements, which is having a capability of shaping the input signal. Okay, so it is a circuit made up of linear elements plus it has the shaping ability. Shaping ability in the sense you give a particular waveform, it shapes into a different waveform. For example, you give a step signal, it will shape it into an exponential. You give a pulse, it will shape it into a spike. So anything it can be, converting one form to another. Now, what is this circuit made up of linear elements? What are the linear elements? R, L and C, resistance, inductor, capacitor. These elements, resistor, inductor and capacitor, can be considered as linear elements. So circuit which is made up of any of these elements are called as linear circuits. So these linear circuits has the ability of shaping the given input. This is what we are going to learn in this subject. So in this unit, we are going to consider this simple transmission network. This can be called as a capacitive coupling network. It is used in most of the circuits to introduce a DC isolation between the input and output. Now, we shall consider the application of a sinusoidal signal to such a network. The output signal of the network will have a wave shape that is a precise reproduction of the input wave shape under steady state conditions. That means if you provide a sinusoidal signal, the output is going to be a precise reproduction of the input wave shape. It's going to be sinusoidal in nature. It cannot become a ramp, it cannot become a square, it cannot become a spike, or it cannot become exponential. So this unique feature of preserving the wave shape in all linear network is applicable only for a sinusoidal signal. If you give a sinusoidal signal, your output is going to be a precise reproduction of the input. But this condition is not applicable for a non-sinusoidal signal. So you should understand this. The precise reproduction of the wave shape is applicable only for sinusoidal input. Or I can say preserving the wave shape is applicable only for a sinusoidal signal. Preserving the wave shape is applicable only for a sinusoidal signal. So on the other hand, in the case of non-sinusoidal input in the sense, it can be exponential, it can be ramp, it can be a square, it can be a spike, anything other than the sinusoidal signal. So in case of non-sinusoidal signal, the input and output shows a very little resemblance to one another. That means if you give a non-sinusoidal signal, it's going to highly alter the shape of the input. You should understand this. So for non-sinusoidal waveform, the input and output show a very little resemblance. To one another. So you should understand this concept very clearly. Having given the simple capacitive coupling network, if you provide a sinusoidal input, the output is going to remain sinusoidal mathematically. Its shape is going to be the same. If you provide a non-sinusoidal signal, it is going to be altered. The shape of the waveform is going to be altered. So this is a fundamental understanding you need to have while dealing with this circuit. Now the term linear wave shaping denotes the process whereby the shape of a non-sinusoidal signal is altered by transmitting it through this linear network. So you should understand, if at all I wanted to perform a wave shaping with this circuit, sinusoidal will not be a useful signal at all. You should understand this. Because if you give a sinusoidal, the output is going to be sinusoidal. So the choice of the waveform is very important. What kind of waveform are you going to choose? You wanted to use this circuit for wave shaping, then you need to go for a non-sinusoidal waveform. You cannot use a sinusoidal waveform. So the definition of a linear wave shaping circuit is, the term linear wave shaping definition, I can say linear wave shaping how can I define it? It denotes the process whereby the shape of a non-sinusoidal, this is very, very important, signal is altered by transmitting it through a linear network. Okay, this can be a precise definition for linear wave shaping. Linear, it is made up of linear elements, RLC, and wave shaping. Such a linear network can perform wave shaping of input provided the input is a non-sinusoidal signal. Now, we are going to learn a little more detailedly about how this circuit behaves for a sinusoidal signal. Okay, so the first important analysis, behavior or the response of this capacitive coupling network to a sinusoidal signal. Now, I told you if you give a sinusoidal signal, it's going to be the same sinusoidal at the output. Its shape is not going to be altered. You are not going to get a square or a spike or anything. But for understanding the behavior in a very deep and a detailed way, it is good to apply a sinusoidal input and study. So that is why we are choosing a sinusoidal signal as the first input. Then we will go for a step how it behaves. Then we'll give a square to the circuit and we'll check how it behaves and so on. Okay, so we'll consider this circuit. I'm going to give an input Vi, which is sinusoidal in nature. And I'm going to check how the circuit would behave for such an input. Now, the behavior of the circuit. Now, having given a sinusoidal signal, for different frequency, it is going to behave in a different way because of the nature of the reactance offered by the capacitor. It is denoted by a term Xc. Xc is the reactance offered by the capacitor. Because of this reactance, for different frequency of the input, the output is going to be different. How it behaves, we can understand by this equation. Reactance of the offered by the capacitor is equal to 1 by omega c. Now, this circuit, this network would act as a high pass filter. Why it is acting as a high pass filter can be understood by this equation. This is the reactance offered by the capacitor. Reactance in the sense, it is the opposition offered to the AC. Okay, there is no point in talking about reactance if the input is a DC. If the input is an AC, the amount of opposition offered to this AC is defined by this term reactance. Now, almost the understanding is something similar to the resistance, but the reactance is pretty more complex than the resistance because this reactance is a function of frequency. Omega is 2 pi f. So it is 1 by 2 pi fc. So since the opposition offered to the AC is a function of frequency, I would say this is a complex a quantity a little bit complex than the resistance. Now we will understand the behavior of the circuit for just two cases. One is how it behaves for frequency f is equal to 0 hertz, and the other case f is equal to infinity. If we understand the condition for these two extreme, then pretty good we can picturize the entire response of the network precisely. Now what happens if frequency is equal to 0? Here Xc will become 1 by 2 pi Fc, which is 1 by 0 when frequency becomes 0. So 1 by 0 is infinity. So the reactance offered by the capacitor would become infinity if the frequency is 0. So what does it mean that the reactance offered is infinity? That means it is fully blocking the input to receive at the output end. So I can very well say the capacitor is behaving as an open circuit for a condition where frequency is equal to 0. So the equivalent circuit can be drawn in this way. Here the capacitor is now replaced with a open circuit. Why? Because the reactance offered is infinity, opposition offered is infinity, so there will be no current flowing through the circuit. Whatever you give here, you will not be able to receive anything at the output end. Okay, so this is the reason why I call this capacitor as a blocking capacitor. The name I give to this capacitor is blocking capacitor because it is blocking the DC input. So you should understand F is equal to 0 in the sense it's not AC, it's a DC input. Having given a DC input, the capacitor behaves as an open circuit. There is no current flow. That means if the input is DC, the capacitor is going to block it. There will be no output here. So this capacitor will act as a blocking capacitor. Now on the another end, we will consider the same high pass circuit with a very high frequency as an input. The very high frequency as an input. So I'm going to assume the frequency is infinity. The reactance offered is 1 by omega c is 1 by 2 pi fc. When frequency is infinity, the reactance offered by capacitor is 1 by infinity. So limit of 1 by n where n tends to infinity is approximated to 0. So 1 by infinity can be approximated to 0, which means there is no opposition offered by the capacitor. There is no blocking at all. Whatever you are going to give will be exactly received at the output end. So how can I draw the equivalent circuit? Since the opposition offered is 0, I am going to replace this capacitor with a short circuit. So this could be the equivalent circuit. When the frequency is very high or frequency is considered to be infinity, that means there is no blocking at all. All that you provide at the input will be exactly received at the output end. Okay, uh, so you would have understood, having given a DC signal, it is completely blocked, so the output is 0. Having given a very high frequency signal without any block, you get the output. So this circuit is gonna completely block a DC, completely allow a very high frequency, and reasonably allow a low frequency. So with this kind of explanation, I can say this circuit is gonna behave as a high pass circuit. High pass circuit in the sense it allows the high frequency signal freely. It attenuates the low frequency signals and completely blocks the DC signal. Now, such kind of configuration, such basic configuration it's the most common coupling circuit used to obtain a DC isolation between input as well as output. Now in the next lecture, we will be learning about the behavior of such circuit to a sinusoidal signal. For understanding the behavior, we will be deriving the transfer function of the circuit. The transfer function will help us to plot the magnitude response as well as the phase response of the circuit. So in the next lecture, I'll be clearly teaching you the transfer function derivation of this particular circuit.